This device, which is actually an electric generator, is an extremely balanced machine. Not balanced in the sense of tipping over, but balanced electromechanically. Now I'm going to show you not one, but 3 new inventions on this machine from quantum magnetics. We'll start at this end and we'll work towards the other. This is a gyroscopic flywheel. It's gyroscopic because 90% of its mass, weight-wise, is located on the outer periphery of this rotor, right in through here. It's the furthest radial point from the axis. These 2 non-magnetic stainless steel rings attached to the polycarbonate rotor provide that weight, and oh my gosh, a huge amount of or moment of inertia when spinning. It's massive. That means you get a powerful centrifugal force and angular momentum for continued rotation even when this thing is under load. Okay, now for the first invention. I have attached right here an onboard 3-phase alternator directly to the gyro. How about that? Because this alternator fits within the space of the outer gyro weight and the innermost axis here, it does not kill the inertia of the gyro when this thing is under load. Just spin and generate. It's a pretty cool thing. Okay, now that leads us to the second invention. On the surface, this thing looks like some kind of common flywheel type generator. I don't even know how many of those actually work, but that's where it stops. Let me demonstrate this. I'll spin this thing up by hand. I'm just taking it slowly because the flywheel is very heavy. The gyro flywheel. Okay, so we're, I don't know, 100 RPM or something like that. Okay, now I'm going to attempt to stop it with one quick grab of my hand. You ready for this? Of course, that would be impossible to do with this massive gyro, but watch what happens next. Look at it. It's oscillating. It's because this is actually not attached to this, as this is not attached to this. The 3-phase gyro and the pulse motor generator actually are not mechanically connected. No belts, chains, or gears. They may share the same axis of symmetry, but they're coupled and synchronized through magnetic attraction only. Like our electromagnetic Earth being attracted to and orbiting around our energy-producing sun in perfect synchrony, that's what this does. See how it resynchronizes itself from that? It'll do that at high speed too, not just slow like this. What does that mean? Open synchronization. That means it is not locked to the shaft of the pulse motor, and therefore is more capable of resisting a change in motion. If the pulse motor stops or is slowed under load, the gyrogen simply continues to spin. The same is also true if the pulse motor gen can spin up to full RPM even if the gyro is held motionless. You can still spin. Look. You see? And the gyro will catch up. Now what you're seeing here is there's actually 4 bearings in this thing, and this is on a separate bearing. And in the kit it's not going to be on a bearing, and that'll reduce a little bit of the friction and even improve the performance even beyond what it's already doing. And it won't oscillate like that. It'll just run smooth with the gyro, and that's what I should have done in the first place. I was just in a hurry to get this prototype built so I could show you and we could start manufacturing the parts for kits. Okay, that was the second invention. Now on to our third invention. Pulse motors typically have electromagnetic coils, repelling permanent magnets fixed to a rotor of some type. All of my previous designs pulsed against both north and south poles of the permanent magnets simultaneously. Many others use only one magnet pole or monopole. But even with my own designs, there still existed a major flaw. This illustration shows a very simple but commonly overlooked aspect of pulse motors and many other motors in general. In most cases, there's a 50% waste of an electromagnetic field indicated by the yellow arrow. For the largest part, a single pole of a coil's electromagnetic field, whether constant or alternating in polarity, is responsible to either attract or repel a motor's armature or rotor. If the coil has a ferrous core, or is backed with a steel plate to help concentrate the wasted lines of flux inward, it becomes counterproductive and undesirably slows or cogs the rotor through attraction. By utilizing both poles of the coils simultaneously with multiple rotor propulsion, instead of the single rotor shown in the center of this illustration, torque, RPM, and a greater electromagnetic efficiency are produced and resonantly directed back through the coil windings for no additional cost of electrical input. And here they are, here and here. Two additional permanent magnet rotors that nearly double the mechanical performance of this machine. How much simpler can it be? I've just shown you three new inventions that you're seeing for the first time and are all based on common sense ideas. We've been dumbed down for far too long. It's time we back up, regroup, and think things through. One final point I'd like to make. This part is not an invention, but a very interesting application. Between the Earth and the Earth's ionosphere, literally a sphere within a sphere, exists electromagnetic waves of extremely low frequency, or ELF, which pulse or resonate like a heartbeat of our planet. This measurable frequency that surrounds all life on Earth is now universally known as the Schumann resonance of 7.83 Hz. Did you know that the alpha waves of the human brain closely match that same electromagnetic Earth frequency? Wow, do you think this is by accident? Okay, that's some of the invention parts, and now let me explain some of the other parts, like the controls. Also pretty important. These two bridge rectifiers down here are connected together, but their purpose is to rectify the AC power that's coming in from the three-phase onboard alternator on the gyro. All right, the top bridge rectifier here is what takes in the power from the pulse motor side, which includes those high voltage inductive spikes into it. Now you can use these separately from this one. These can charge batteries on their own. These can be put back into the system because it's on a separate circuit from this here, which goes to that. You cannot feed the power from this back into the system that runs the pulse motor. Electron flow does not want to work that way, so you can't do that. But you can port this back in any place you want. Okay, and so here you've got a little terminal strip here, and up here this is new. Let me see if I can zoom in on that. There we go. All right, this is a potentiometer here. I probably have one that's a little bit overkill on this, but I've got pulse and then amps high and low. That's turned on through this switch right here. If it's down, it's in a common fixed position with fixed resistors that will run this thing at a fixed speed. Well, it's also dependent on how you adjust your distance on your read relay over here on the timing circuit, and we'll touch base on that in just a second here. So anyway, but what this does, if you flip this switch on, it will and it'll switch it off of the common resistors and go to this potentiometer, which allows you to adjust the current that's coming in. Now basically what that does is it's affecting the pulse duration on the trigger side of your solid state relay. So it's cutting it way down. But for the layperson, I figured if I put something on a label that says something to that effect, they're not going to understand it. So I've just got pulse, amps, high and low. Simple. And it doesn't turn much. It may turn this much and this much this way, and that's about it. That's why I say I'd probably use a different potentiometer. But I've got some for kits, so they're ready to go. Okay, so of course your power on, and then I'm spinning the shaft a little bit. It shows you when it starts to pulse. Okay. So that's that. Turn the coils on. We're going to do that in a second, so just bear with me for a minute. I just want to go over that. And obviously this will show you what the voltage is that's coming in. Let me back off in this a little bit again. It shows you what the voltage is that's actually coming in for the pulse motor itself. And then your current can be adjusted again with this, or in the fixed position here, your choice. Both of them work really good, but I like the fine-tuning of this because you get some really incredible stuff happening. Okay, so you got DC-DC converter, same as the T2, and it's fused, and that's about it for that. Over here, we've got the conventional timing disc, and that I've had on many of my other machines, and the reed switch here. But here you'll notice that there are only 3 magnets instead of 6 that are going to engage. There, there, and there. Okay, I just wanted to quickly point out the third invention here, which you see the another one of the additional rotors spinning here with the magnets going past the coils on the outside of the coils. A very cool thing. But with the output not being directly locked to the input, this system becomes open. When we apply the powerful electromagnetic pulse to this motor every 120 degrees, because we're skipping a position every other magnet, then the open core pulse motor itself freewheels nearly 50% of each rotation. It adds to the overall mass inertia, the mechanical mass inertia and momentum, and a non-mechanically connected dual flywheel type condition. Hey, that's just another first from quantum magnetics. There's my plug. Okay, I'm spinning the machine up by hand, and granted it's an open circuit, but I'm going to use this patch cord and just plug its output back into itself, just so that you can see on the meter what kind of current it potentially has. And this is, whatever it is, 50 RPM. You can see it quickly jumps up to 3 amps. So if you can imagine it at 500 or 1000 RPM, if it's driven by another machine and you don't put power into this to operate it as itself, but just as an auxiliary generator, it's very powerful. Again, there it is. Okay, I've fired this baby up off camera because sometimes it takes 2 or 3 minutes for the gyro to actually sync with the pulse motor, so I spared you that extra time on the video. It's already too long. But I've got a little bit of input coming in right now. It's just 12 volt input, because otherwise it's just these 3 cap modules back here in the back. I don't think I showed you that, but you can kind of see them. Anyway, so we can unplug the input and just run on the caps, and it's kind of cool that way, and it will run for a pretty decent amount of time. But I want to show you here the switch over here. Now this is on the fixed resistors, and when I flip this switch up, now it's on the potentiometer, and watch, I can adjust it. I got to be really careful. I can adjust it down to 50 milliamps if you want to run this thing at that. Talk about not using much power and still being able to generate it. This thing is just beyond what you can imagine. But crank it up to 1 amp, take it up higher. I mean, I can take it to 3 amps, but I don't want to waste the energy. This thing will go, I think it's about a 1.5 amps. It'll crank up to close to 1000 RPM. So you've got the ability to take it up fast if you want, but I prefer the Schumann frequency over anything else, and you probably will too. You'll see.